Welcome to the 10th session of Computer Networks. We are studying the circuit programming in C, and today we will be covering the multitasking TCP servers. Firstly, we would like to understand the use of the process. Before that, let's explore the idea of simultaneous multiple processes. The idea of a multitasking server is for making it possible multiple clients to connect and exchange data with the same server at the same time. What does it mean? If you recall the Echo server previously, when we were creating the TCP server, and then we were creating a client, and when we were calling the server from a single client, it was working fine. But when we were running two or three clients at a time, and with the two or three terminals, then only one client, the server was responding to only one of its client. But if you were trying to call from the three or four clients, then it was not responding to the other of the clients because the server had made a connection with one of them. So in that case, we had only one process established between the server and the client, and it was not possible for the server to support multiple process or to accept the request from the multiple clients at a time. Please remember, I'm talking about the TCP, I'm not talking about the UDP. So to resolve that issue, how about we have the multi-processes or multitasking server such that the server accepts any request coming from any amount of clients, and whenever a request is there from a client, it will just make a child process for that client, and that client will be serviced. If the other clients comes, then another child process will start for him, and then again the next client will also be serviced. And when the first client wants to terminate its process, it will just terminate its previous client, and if any other client is coming, so that client will be again giving some service. To sum up all, what I mean is to make it such a dynamic process that any amount of clients can contact with the server at a time, and the server is able to support all the clients at a time. One of the good example for this is the chatting service messengers. When you are using the any messenger like Kakao or WhatsApp or any other messenger, at that time you are using one server or a specific server, but multiple clients or thousands millions of clients are connected to their server at a time, and the server is able to provide the services to each and every client. So today our goal is to make such a TCP server such that it can support enormous amount of clients. Let's first understand what a process is and what is the process ID. Process is whenever something starts on your computer or application. For example, application is running or anything start on your process, the your operating system, the kernel inside your operating system, it will give some process ID to that particular process, and this process will be recognized with a certain specific ID. So processes are basically a running program, and each process has a memory resource allocated for it. So it's not like process is running and it is not consuming anything. There is no free lunch. Everything you are doing on your computer, it will always occupy some of its resources. For example, it might be using part of the RAM, part of the processor, and part of the other resources. Each process has memory resources allocated to it, and then multiple processes can run at the same time. So that is also possible. And if there are multiple processes running at the same time, each process will be assigned with some ID, and that is called the process ID. Operating system always keeps numbering the new created process for a process management. So in case you want to kill the process, or you want to join a specific process, or you want to do something with that process, that is called process management, and for that sake the operating system allocate a specific process ID. So if you run a command ps underscore au, this command will execute certain things like that you can see here. For example, the user might be root, or it might be some other thing, and then it will also be assigned with some process ID. So this is what I was talking about. For example, this process is being given 4400 ID, then the next process is being given 4401 ID, and so on and so forth. So each process, which is this one, this is a command which is running here, and it is occupying a process ID, and it is consuming this much of processor and this much of memory. So these are the resources which has been consumed by this one. So here the process is 0% used, but the memory is used a lot. But if on the other hand we see some other command which is user and this something blah blah blah, in that case not only the memory is being used but also the CPU is used. So to create a process, there is a function which we call fork function. The fork function creating a process through a function call. And whenever you want to have this fork call, then in that case you will need the unistd.h. This is the built-in kernel header file when you are using this fork function. Let's see how does it works. Here is a generic example. We will see it also now in the practically, but let's see what it is doing. Here we have declared a variable which is a global variable, and we assigned it some value, and then we started the program with the main, and then we also declared a local variable which we called lval, and we assigned a value 20, and then we just incremented the lval with +5 and gval ++. Here we called the fork function. The time when you create a fork function, it creates a child process, which is this one. So this child process basically can access all the variable that you have declared here, and it will run alongside the parent process, which is this one. So from now on, when you started the program till this point, only one program was running, but at this point now it will become two. One is the parent process, which is this one, which is running by default, and the other will be the child process, which will be running alongside here. So this one was the parent process and this one will be the child process. So the child process will be, well, when the child process is running, it will be also using the same variables that the parent process was running. So the child process is always allocated the zero PIDs. When you call the fork function, that time it stores the process ID here, and the process ID for the children process is always equal to 0. So the if it is equal to 0, it will increment the gval plus plus, and if it is not equal to 0, it will increment the lval plus plus. Let us see a fork process and practical, and then we will come back to the slides. Today I have all the C files ready here, so I don't have to type each and everything. I will just be explaining you everything that is required, and you have to understand it, and then I will also give you the source code. You can make some changes in it and you can further explore it. So let's go to the, firstly let me take this fork.c, and then let's go to that cygn64 home, and then my username, and finally here you should paste your fork.c. Let me open this fork.c. Here you can see that unistd.h, which is used to support this function, and then I declared a global variable which is 10, and then I will start my main function here. So I also declared a local variable which is 20, and then I just incremented it like that, and here I started the for function, which means that from 11 number line there will be two process starts. One is the default parent process which is running here, but here alongside another process will also start, and it will be running in your RAM, and that process is your children process, and that process will be assigned with a process ID 0. However, your parent process will be having some other ID. It can be rand, I don't know what it would be. You can just type the ps space au, and then you can see what is the process ID for that one and all those stuff. So we will see it later on, and then you can just go and put a condition here. So my condition is, if it is a child process, for example, if it is a newly created process, then just increment the gval with 2 and also the lval with 2. Else, if it is the parent process, if it is not the child process, in that case just decrement the gval by 2 and also the lval by 2. Once we are done with this, then we can also put another condition so that we can type the values of the parent process and also the value of the child process. So in that case, the child process, since its id was 0, in that case we will put the value percent d here from the gval and lval. So let's expect the value from here. Gval was declared as 10, and when the 2 was added, what would be the value here? It would be 12. And likewise the lval was declared as 20, and then 2 was added here, so it could become 22. So it will become 12 and 22. And then here, and on the other hand, this gval was 10, so when it is decremented by 2, it will become 8. And lval was 20, and when it is decremented by 2, it will become 8. So what we would expect in the child process should be equal to uh, 12, 22, and the parent process should be equal to 8 and 18. So let's run it and see if we can see what we are expecting. So I will go to the desktop. I'll run the cygwin terminal. Let me zoom it. And when I run the fork, so it gives me 13, 27, and 9 and 23. So I believe I didn't count these lines. So what happens here? Gval was declared as 10, but here it was incremented by 1, so it become 11. So when 2 was added to it, it becomes 13. Lval was declared as 20, and when lval was incremented by 5 here, and then here it was incremented by 2. So in this process, 20 plus 5, 25, and then plus 2 is equal to 27. So we are expecting here 13 and 27 for the first one. And likewise for this one, gval was declared as 10, and then it was incremented by 1, so 11. 11 minus 2, so it should be 9. So the first number should be 9. And then the next number, the lval was declared as 20, then it becomes 25. 25 minus 2, which is equal to 23, and it should be equal to 23. So it is the child process, which was the first process where the PID was equal to 0. It is giving me 13 and 27. And the next one, which is the parent process, and it is giving me the 9 and 23, which is as expected. So coming back to the slides, and let's see what is a zombie process. So when your child process is started and it keep running, as I told you, it is using your resources. And when it is using your resources, the parent process or the main process which has lead to these children process, that is responsible to kill those child processes. And if it didn't kill the child processes, those children becomes zombies. I think you probably know what a zombie is. So a zombie is something like this, a horrifying organism. So the zombie process is a process that has completed its job but not yet cleaned up. So sometimes you just run a fork command, and the fork command give rise to another process, and that process is running for certain amount of time, and once it accomplishes its job, then it should be turned off. It should be just you should take it down. But if you didn't turn it off, then at that time it becomes a zombie. It will keep running and it will consume some of your memory resources. It depends on what kind of process it is running. If it is like a very bulky process, then in that case it can use much of your resources. And if you're running it again and again, the processes, then in that case it will become redundant. And if it become redundant, then it will put more pressure on your cpu and also on your memory, and your computer will become slower. So every time the main program or the parent program, when it starts some children process, it should keep tracking those children processes, and once it is completed, it should just kill all its children processes. So if not cleaned up, it consumes some amount of your space and memory alongside a process id number it occupies. It's the responsibility of the parent process to clean up its zombie children. So it should just shut down its bad children. which are the zombie children's. Once the children process exits, it passes a return status code consecutively. If the parent process doesn't destroy it, it will turn into a zombie process. So how to create a zombie processes? Let's create a zombie processes, which means that we are going to create some process and I don't care about it. I'm just creating it. I'm not killing it. So once the zombie process is started, it will just keep running. It will become a zombie for me. So I can take another example from the zombie. I'll copy it to the same folder, which is this one, and I'll paste it here, and let me execute but before executing it, let's see what is there in the zombie process. The zombie process is shown here, and here you can say that the firstly the process is created, and then if the process is equal to 0, for example it is a child process, it will say that I'm a child process, and then I keep running it, or I'm just sleeping it, or I can do any function here. For example, I'm do some very long calculation or anything, and that is still running, which means that the child process is running here. And else the there is a parent process if it is the PID is not is equal to 0, which means that by default it will be a parent process if the ID is not 0. In that case, the parent process will just wait for the 5 second, and then I have to display whether is this finished or not. When this one is finished, it will then just print that the child process is finished, and then if this one is finished, then it will just say that the parent process is end the parent process. If we look at this one, it has to run for 300 seconds, which is a huge delay, and here it will only for 5 seconds. So the parent will stop, but the child is still running. In this case, the child is acting as a zombie. The parent stopped doing its working, but the child is still running. It still keep working. So it will still consuming some memory there, or it will still consume some resources there. So let us see how does it works. I will firstly execute this one, and once it is executed, I will run it, and I am a child process, and then the process is still running. And if I think I didn't correct the naming of this one, and if I open it, parent process, I'm a child process, okay, and the child process, and since it's not ending, so it will keep running. Oh, sorry. Here, I have to put this one here. I will say sleep for 300 seconds, and this will be sleep for 5 seconds, and I will just save it, and then let's exit it. I think I was saving it in the wrong file. So, no. Yeah, this one, Control S, and let's save it. Exit it, and let me run it again. Sorry, I will show you this thing later, and let me do it again. And once I'm running, so the parent process is finished, but the children is still running, and the children process is keep running. However, the parent process is finished. When the parent process finish, it doesn't care about the its children process. And if I, for example, let me clear it out, and I will say that TSAU. So if you look at here, the zombie is still running. Can you see it? There is still one process running with the process ID 1094, and there is something running there, and Muhammad Salman and the zombie is running. However, the parent process already finished there. So the parent process finished, but it didn't kill the child process, and it's still running, and it will run for almost 300 seconds. And once the 300 seconds are finished, then this will be finished. You will not be able to see that anymore. It will keep running, it will keep consuming your resources. And let's go back to the slide. So I think there is a little bit mistake. Firstly, you have to put some delay here. So you just put some 300 or some long delay here in the child process and reduce this delay. In that case, the parent process will be finished, but the child process will still be running. And if you verify it with the PSAU, the child process is still running because it becomes a zombie process. So in that case, the zombie process has to be killed too before you want to exit or you want to finish the parent process. So we will see how we can do that, how we can handle that. To do that, to handle the killing of the either killing of your child process or keep waiting for the child process to finish a task, then there is some command which is called waiting. We can keep waiting for our child so that our child finish his task, and once the child finish the task, then we can finish the process. So here is an example, and I'll prefer to just execute it here. So I'll go and take the wait dot c from here and I'll paste it here. So let us see first what is inside the wait and then we will run it. Here the fork is started, so which means that the process has been started. And we say that if the PID is equal to 0, which means that if it is a child process, then exit it, return 3, which means that it is properly finishing the process. Before, we were not exiting it or we are not returning it, but we were rather giving it some delay and we put some text there, so it was printing that thing and it was about to take 300 seconds. But here we are going to return it. It's going to be killed. When it is killed, it will be returning 3 value, and else if it is not a child process, if it is a parent process, then just type the PID of this one, the child process, and run an other PID process in other process. So this is process within process. Now the parent was running the first one, and once that is finished, and the second one we are typing it, that is the PID, and then we are again running the fork process, so again another PID will be assigned to it, and then again we are saying that if it is the child process, then exit with 7 number. I'm writing 7 just because to make it distinct from this one. It will be showing 3, so it will be showing 7, and it will properly exit. And else if it is the parent process, then in that case also type what is the PID of the second child. So here two children are there. One is the first child that was created there, and here is the second child which is created here. And then here is the wait process. So what the wait means, we have declared the status here. Wait is basically pointing towards the address of the child process, so it will keep waiting for the child processes, which means that it is pointing towards the child processes, and if it is still running, then it will check WF exited. I have defined it here that this is the macro that returns a non-zero value if a child process terminates normally with exit or exit. So it basically gives us a non-zero value if it is exited normally. So in first case it had returned 3, so it will shows that child 1 is this one, and in the second case it has returned 7, so it will shows us the 7 value, and then it will sleep for 30 more seconds and then the program will be finished. So let us see how this program works. Here you can see it will type the child ID of the first one and the PID of the second child. The first children was exited with 3 and the second children was exited with 7. So I advise you to carefully take a look at this program, and to understand it more clearly, you have to make some changes in it and keep doing some more practice on it and try to understand how the fork starts. And I have some more ideas for you. So once you create the fork here, and right after it in the next line, when you create another fork here, what will happen? So can you just try that and see what is happening there? Or it is rather a very complicated program. You can just type, for example, you can start from a very simple program. You just say that start from the fork, and then type, for example, hello world, and then exit it, and then start from a fork and then make another fork and then type a hello world and then exit it. And then while doing that, like start from the one fork, and then you not only type the hello world but also print the id of the fork and then exit it, and then make two fork and then make the right type the id of the fork and then exit it, and see what is happening and what did you conclude from it. So waiting for a specific child process to complete. For the waiting, we have the sys slash wait.h header file, and from there we can have two kind of waiting. One wait that we just saw earlier here, they wait and then pointing towards the address of the child process, and the other one is the wait PID. So what is the difference between the wait and the wait PID? The wait system call suspends the execution of the calling process until one of its children terminates. The call waits and status is equivalent to wait minus one in status and 0. So I'll explain you what it is. And then there is a wait PID. So this means that if any of the process is killed, so it doesn't matter which one, but if any of the child process terminates, then this works. And the one we suggest earlier, wait and status, it is equivalent to you use this one with the input arguments of -1 and status and 0. If you make this one, actually the wait PID syntax is like this. So the wait PID require the PID of the process, because this wait PID process system call suspends execution of calling process until a child specified by a PID argument has changed state, which means that you have to put the ID of the process that you want to kill. By default, the wait PID waits only for the terminated child. The wait PID here, you can see that which process ID you want to kill. I showed you when you put the ps space au on the command terminal, it will gives you the processes ID and it is running there. And sometimes it also tells you like what is the memory consumed, what is the CPU consumed, and then it also gives you some more options. But if you don't want to use the wait PID and you want to use it as a wait, then you have to put this one as -1 and this one is in status. So when you put that one in status, and then you have to put also this one as 0. So once you put those three arguments like this, then it becomes equivalent to what we saw earlier, wait and status, right? But if you want to kill a specific PID, then you have to put the PID there, the PID of the process here. So let's look at this call. Here is a new function used, the and the options. So if you see the options here, this is the options here. So here we have used W no hang. It returns immediately if no child has terminated, which means that don't hang the process and just return if any of the child is finished. So I'll take the wait PID from here and then I'll copy it here, and let us see what is there inside the wait PID. Since we are using the wait function also, so we have also added the header file for that one. And while starting that, we can see that the fork process is started, and then we say that let's say the PID is equal to 0, so that means that it is the child process. For the child process, we will sleep it for 15 seconds and then we will return 24 number from here. Else, if this one is still running, so which means that if this, until and unless this one is running, then you don't have to exit from here, you have to keep executing this one. Once this one is stopped, once this one is finished, then we have to get that value and then we will exit from here, and then we can print out what was the status of this one, which should be 24 value. So let's see and how it works. So let's keep waiting, and then for 3 seconds, since it's still running, the that was 15 seconds, so it will keep running until the 50-second child process is finished, and we can count it here: 1 2 3 4 5. So 15 seconds are done, and then once the child process is finished, then the wait will exit. The wait will finish the parent process. So the parent process is not finished earlier than the child process is finished. So it has to make sure that all my children process finished, and once it is finished, then it will exit. So this makes sure that my child process is not turning into the zombie process. And you can take a look at here. So here the child process was starting from 15 delay, right? So uh, from 15 delay, this one is keep looking, since it has used this one option, so it will not be hanging, but it will check if this is still running. It will check here. Oh, it's still here, so it's still running. Don't exit from here. So it will keep waiting for it, and then again it will check. It's finished, it is 15, and then again it will check. Oh no, it's still running here. So once it is 15 is reached, then here it will just skip this one, and then it will just see what was the value returned from that child function, and we just display it here. So I think it is not complicated, maybe a bit confusing, but you have to just go through it, just do more practice on it, and then you will see it's still working. So here you can see that our output we saw was 3 second, 3 second, 3 second. So each time this function was looking for this one, is it finished or not? If it is not finished, then just keep waiting. Finish or not finished. So this is just show this thing, but yeah, still please wait. So this is basically informing the parent process that please wait, it is still running. Please wait, it is still running. Please wait, it is still running. Oh, it is finished, now you can go. So it holds the parent process until the child process is not finished. Now let's talk about the signals. There are some signals that can be used to generate some interrupts. For example, if I give you an example like ping 127.0.0.1, and it will keep running forever. So if I press the control C window, sorry, if I run the control C command, I can interrupt it in the middle. So in that case, control C in my case is the interrupt, or it is the signal for the interrupt. There are a couple of signal commands in C, and you can just Google it. SIGHUP, it is for hang up the process, and if you use this one, this is for interrupt the process. Sigil, this is illegal instruction. So these kind of signals you can send to your program, and that program can work accordingly. So we can use these three commands here in our example. For example, sig alarm is used for the alarming signal. Then sig int, it is kind of control C, which interrupt your signal. And sig child, that we will be using in our process to monitor the child event. And if it is already terminated, then it should be signal. In order to receive the signal from other process, a process must register to the signal code. So we have the signal registration here. The signal registration here require a header file, which is signal.h, and there is something which is the handler. So don't be afraid of it. We will be using it in our program, and it will not be that difficult, as much scary it looks like here. A signal is a software generated interrupt that is used by a process or operating system to inform another process about the specific event. Some process like this: sick child, my child. When the process is terminator, call my child function. So when this process is terminator, sick child means when the child process is terminator, then you have to call this function. So this function you can declare in your program. Or when this if the user press Control C, call key control function. So if anyone press the Control plus C command and try to terminate the process, then this function should be called. So here we can see a very simple example to see how the signal looks like. So basically we are using the sig alarm, which is the timeout, and sig int, which is the key control. So whenever you are calling some function, you have to define it. So here the functions have been defined. Here is the body of our main program. And firstly, we are just signaling the sig alarm, and the sig alarm is after specified time interval by sleep finishes, operating system sends the process sig alarm to wake it up. So regardless of that sleep mode, this sig alarm will keep interrupting, and this will keep sending the message, or this will keep awaking the process. So we have a process which is starting from I is equal to 0, I is less than equal to 3, and I plus plus, and then uh, it is it will put the wait, and for the wait will keep waiting for 100 seconds. Whenever the first iteration is executed, although this is to wait for the 100 second, but this will not wait for the 100 second because the alarm has to be wake up for every 2 seconds. So every 2 seconds it will keep checking, and then again this process will be executing, and then although it has to sleep for this, but because of this alarm it will again wake it up, and then again the process will be executing. So let us see how it looks like. Let me delete all the junk programs that we saw earlier, and let's put the clean program here. So here are our two functions that I just explained you before, the key control and timeout. So they are just simple functions. Here is the main body of our program. So the main body of our program is signaling these two programs that we have defined here in the body, and then it is alarming it. So every after 2 seconds, although this is to run for longer, but every after 2 seconds it will keep checking for these two. Regardless of its long wait condition, this alarm will just awake within 2 seconds. It will check for both these signals. So these signals are defined here. For example, the timeout signal is defined here, and this one, if it is time sig alarm, so in this one it will just put the timeout, and then again it will alarm. The other one is key control, but since we haven't pressed any Control C in the middle, if we press the Control C button in the middle when this program is running, then it will also type that sig is equal to set this one, and this one is used for the Control C, and then it means that it has been forcefully terminated, so it will just type something like that. So let's run this program again and see also the effect of the Control C. So this one, and at the middle I just pressed Control C. Sorry. So when I press the Control C, it say that Control C pressed. Cleaning up the zombie child process is very important. You can see this society here. Here the other people are laughing at this parent because the children has been turned into zombies, but the parent is careless enough that he is not bringing his attention to the children to risk them. So these people are saying that what's going on with the zombie processes? Their parents are too busy to get any notifications. Although if this parent was unwise enough, he would have taken care of his children, and once their process was finished, he was taken care of them, and like he would have killed their processes, or he would have finished their processes. Since he has not finished their processes, so the children were turned into the zombies. So to clean the zombie process using the signal, this is a very elegant way rather than we also saw there in the previous example where we were waiting for the zombie process to end, and once the waiting condition was met and the child process was finished, then we were closing the program. But here we are doing the same process, almost the waiting thing, but using the signal. Here we can start our main program. So basically the signal action is started with a structure which we call act, and then we do the handler also with the act, and all the act, what is the SA mask of the act, and what should be the flag of the SA flag of the act. So there could be different kind of associated things with the signals. Those things can be configured using the structure, the sig action structure. And finally, and we can say that perform the sig action, and then what sig action, that should be sig child. And then we saw what is the sig child. Sig child was the keep monitoring when the process is terminated, when the child process is terminated. So that sig child, so keep monitoring on the processes of your children, and then act accordingly. How to act according to the structure you have filled up here, and there is no option. So just do this one in the main program. So in the main body of the program you have to perform this task, and then you have to also see the status of the child, that what is happening to the child there. So the signal is coming to the child, and then you have to see what is the child doing, is it finished or not. If the children is finished, then you can returns the ID of the children, and also you can say that what was returned from their children, what was the output, or what was the exact value from their children, or return value from their children. So to clean up a zombie process, you should simply wait and get the result code of a child process. Now let's combine all the concepts using the TCP server, the TCP echo server that we had seen before. So we saw everything chunk by chunk. Before we saw what are zombies, how to keep waiting, how to kill the zombies, how to kill the zombie processes, and then how to wait, how to do that when you have to kill the zombie processes. What is the process to kill the zombie processes? Then there are two processes. Either you can do the wait, or you can use some signals. So once you do the signals or waiting and those stuff, let's merge it together and integrate it into the echo server TCP that we did before, and see how these things are all working in parallel. You can see that this is the TCP server, and if any client request is coming from here, it will interacting with the TCP server, and the TCP server will spawn another child process for it. For example, this client requested to the server, and the server make a child process for this one, and now this one can establish a connection with this one. Likewise, there is another process, or there is another client coming and sending a request to the server. The server will accept it, then it will create another child process for the other client. Basically, multi-processes based TCP server creates separate processes for each client. After each client will communicate the one-to-one server process. So multi-process server example. Here is the Echo MP server example. The server is accepting a request from the client, coming from the client, and if there is no client, then you just close the client. But if there is a client, then create a child process for the client by using the fork. And once the child process is created, if the PID is -1, which means that there is no child process created, then again close client socket, there is no client at all. But if the child process is once created, then close the main server. We will see the reason why we are closing the server socket, because the function of the server is only to accept the command coming from the client, and once the client is already accepted, then another child process is started for it. Now the child process is responsible for running that, or for the executing all the functions here happening here, not this server socket, because the server socket was only accepting it. It has not to do anything with the executing, or it has not to do anything with the servicing the client. So that's why we don't need the server sock anymore. And then this is the echo process, reading from the client and writing back to the client. And finally we are closing the client when this is done, when this process is done, and then client is disconnected, return, and finally everything is finished. The parent process leads to the child process by using the fork, and when fork is called, the whole memory is duplicated, which means that not only the parent process but also with the child process starts, meaning that also the server and the client socket descriptors are duplicated, but we don't need the duplication of the parent and the child. That's why we are finishing this one that we saw here. So we have to finish this one, and if there is no client socket, then we also have to close this one. So we have to finish this one, and we need to remove the unnecessary socket descriptor from the process as follows. Server socket goal is to only accept the connection, so remove the client socket descriptor. So here the goal was only to accept the connection. The server socket goal was only to accept the connection from the client, nothing else, because there is a fork running here, and once the fork is started, it means that a child process already started, and that can take care of the client. The goal of the client socket is only to exchange the data with the client, so remove the server socket descriptor. So take the MP server and the MP client here. So basically there are two things. One is the echo client and the other is the MP server. The MP client, it is exactly the same with which we had seen before. So we have done nothing here. The MP client is exactly similar to the previous client, but we have done some changes in the MP server. So in the MP server, we firstly do all the processes because we have to create the socket, we have to then do the binding process and all those stuff. But alongside that, we also have to use the uh, one more structure here, and that structure is responsible for the signal handling that I showed you before. So if there is a child process running here, and once the child process is finished, that should be informed to the parent process that the particular child process has been finished. And if there is a new child added, then also that should be informed to the server that there is a new child added by using the fork. So when there is a child added there, the fork is doing that. But when the child is terminating the process, this signal action will do all the process. Then we have the socket creation, then we have the server address and all those stuff, and then binding, listening, and all those things is happening. Once there is an accept coming from there and the accept is not empty, it means that the client has sent the request and the server has accepted the request, and right at that moment the PID will be starting. The PID means that the new process of the fork will be start, and the new process of fork will close the server because we don't need the server anymore. The server purpose was only to accept the client, and that is done. So just close it. And now we are reading from the client and then we are writing back to the towards the client. And once this process is done, then just close it. So almost everything is similar. We have only added two things. One is for the signal so that we can get the signal action, and the other one is the fork, which makes a new child process for each incoming request. So let us see how it works. I would like to run 2 3 terminals for this one. For example, one can be a server and the other can be clients. The previously we saw that the echo client was able to handle only one TCP client, but here it should not be the case. It should be able to handle as many clients as much we want to interact with. Now let's say that this is our server. So we will start the server here with the port address 1234. Now my server is running, and now I will start my client, and the client is 127.0.0.1 and then 1234. So as I click it here, it will create a new client here. And at the meantime, I'm also creating another client with the server. So when I want to connect another client with the server, again I have to do the same thing. Sorry, not client, it is the client. So CLIENT. So the two clients connected here. So new client connected, new client, as much as we are adding the new terminals, it will be, and we are calling this address, it will be connected to the server. So if I write anything here, see, it is responding. At the same time, I'm also writing something and it is also responded here. That's good. And if I want to quit from here, either by pressing Q or Control C, when I quit from here, it means that the child process is finished. And when the child process is finished, the parent is aware of its child process thanks to the signals, and it will just show the ID of the child process that has been finished. And thus we can again connect to it by using this one, and again we can do the process, start the process by using this one, and then we can instantly make a connection, or we can instantly communicate. I don't know where my cursor is now. Okay, yeah, and the same thing is here. And if I quit from here, it is finished. And again I quit from here, it is finished. So also see, although it was the same terminal, but when I am sending a new request from here, then it will be sent with a new process ID. So this process ID is not common at all. So every time I'm calling the server, it will be assigned with the new server ID. And once I'm killing it, it will be the server is aware of its killing process. I would like to show you one more beautiful feature, which is this one, multiprocessing client example. So far we did everything with the server, but we didn't do anything with the client. So in this case, our client is a kind of half duplex, which means that we send something to the server and the server write that thing and then it read it back towards the client. So which means that at a time we can read or write. So we cannot do both the things at a time. When the writing is there, the read operation cannot be performed, or when the read is there, the write operation cannot be performed. But sometimes it can happen that the server, you are downloading, for example, 1 GB file from the server. While that file is being downloaded, you are also simultaneously or at the same time sending some messages to the server. So you are not only downloading the file from the server, which means that you are not only reading from the server, but at the same time you are simultaneously sending the messages there. Before it was half duplex, send data, echo, again send data, echo. So once you send the data, the echo is responded. Again send the data and echo is responded from the client and the server. But what if we have a full duplex communication? The client is not only sending the data, but at the same time, it is also receiving the data. And there is no conflict at all between the sending and the reception of the data. To do that, we have to make some changes in our client, which is the echo client, MP client side, which is the echo client side. So once you send the connection request, and that right at that moment you have to make another process, and the other process will be responsible for, one process will be responsible for the writing and the other process will be responsible for the reading. So which means that the child process is which mean in this case the child process is responsible for writing in the routine and the other one is responsible for reading. So here is the function, the read routine and the write routine definition, and we can see that it is almost the same program that we have seen before, but only with a separate line. So we are performing this function in the read, and then in the other process we are performing the write operation. So if we see these files, for example, if we pick the MP client from here, yeah, if you pick the MP client from here and paste it here, and then we see what is there inside it. Here you can see that we created the PID here once we send the connection request, and then we defined two functions, which is the read routine and the write routine. And the read routine and write routine both are distinctly defined here, and then we are just splitting the, before the read and write was all together, but now we split it into two, main function and the child function. So I'll start client and server again. Let me open up two or three more terminals. So for the MP server, we already have the executable file here. But for the MP client, sorry, not the client, the MP client, we have to execute it again. So I will just do it like this. I don't know what the full name is, but let me see what is the full name. Echo underscore MP client. So EC. Okay, and let me call it client. And now let me run the server here, server, and let me say the port number is 2222, and now the server is running. And from here I will just run the client and then 127.0.0.1, and no, it is not 120, it is 127. Seems like I'm tired. And then I should put the address 2, so the new client is connected. That's good news. And then also the 2222, and it is also connected, so I can see it is happening, and also this is happening. But to see that is it a separate process from the client to the server or not, so let's also verify this thing, right? I think it's better to verify it. So I will say ps under ps space au, and if I see, if I zoom it, or if I maximize the window, then I have 1, 2, 3, 4. So I have 4 client processes from the 2 client windows, which means that it has one read and one write, and then also it has one read and one write. So it means that 1, 2, 3, and and 1, 2, 3, 4. 1, 2, 3, and 4. So I have 4 clients there, and then the server are the serving all the 4 clients. So it's for today. It's already 12 a.m. and it's too late. I hope you enjoyed today's video lecture session. I would recommend you to do more and more practice on it. Thank you so much for having your attention.